Okay, so welcome back to our Aerospace 291 lectures. I haven't got the roaming mic, so I'm going to have to try and speak into this one, but I think it'll be okay. So today what we're going to do is kinetics. Okay, so this is the last of the lectures in this series on sort of classical mechanics for rigid body dynamics. Then after this, we're going to move on to do sort of rotational dynamics. We're going to do balancing and gyroscopes, okay, which also use some of this theoretical framework. So remember that we've already done kinematics, so this is different. This is kinetics, okay, so easy to get them confused. So what is kinetics? It's the relationship between motions and forces. And so when we try and solve a problem in rigid body dynamics, we're going to go through this type of process. First of all, we're going to solve the kinematics. Okay, so that's what we've already done in the past lectures. That's the relationship between the motions. Okay. Then normally what we would do is then we'd draw some type of diagram. Okay, so that's all pretty standard, isn't it, to solve a problem. And then finally we would apply the governing equations, okay, to solve the kinetics. Okay, and so we've got two choices with governing equations. We're either solving the force equations, and so that would involve linear accelerations, or we'd be solving the moment equations, and that would involve angular accelerations. Okay, so that's the kind of process that we go through. And of course we know that for linear motions, we can apply Newton's second law in the form that we know it well. So that's usually written in this context as the sum of all the force vectors acting on a body or a mass is equal to the mass times the acceleration vector. So in this kind of classical mechanics, this is also rewritten sometimes as, instead of the acceleration, we write it as d by dt of mass times the velocity vector. Okay, because in classical mechanics we tend to work with velocities very often. Okay, and mass times the velocity vector is usually called the linear momentum. Okay, so this is actually the linear momentum vector L with a dot above it because that represents the d by dt. If I notice that on Wikipedia now, their notation is almost the same as mine, except they call L something slightly different and they have a slightly different notation for this. But if you want to look, the Wikipedia page is actually pretty good for this this derivation, except, as I say, there's a slight difference in notation. So if we say where L equals m times v is linear momentum, so that's linear momentum. We also have angular momentum as well. Which we'll denote as a vector h0. And that's, we can consider that as the moment of L around a fixed point. Okay, so the fixed point is 0. So let's draw a picture just to show what that might look like. So if we have a three-dimensional space, x, y, z, which of course we're using as in the ijk formulation, but let's just leave it as x, y, z for now. Okay, and we have a mass m, okay, so a point in that 3D space. So we've been defining the vector that goes from the origin or point O to the mass as r, haven't we? And then the mass is moving with some velocity v, and so the angular momentum h0 is equal to r crossed with mv. So to be able to put these expressions into the Newton's laws, we need to find the rate of change of the angular momentum. So we actually need to take the derivative of this with respect to time. So we need dh0 by dt, which is equal to d by dt of r crossed with mv. So, and as the mass is moving in space, both r and v can vary with time, can't they? Because r is the distance from the point O. So we have to use the product rule for differentiation again, in this case. So what we get is r dot crossed with mv plus r crossed with mv dot. But of course r dot, the distance vector times d by dt, is actually the same as v. So that, and as you know, the cross product of a vector with itself, because m is just a scalar, okay, is 0. Okay, so this actually goes to 0. And we have this other bit left, which is r crossed with mv dot. So let's just make a note of that. So note v crossed with mv equals 0 as the vectors are in the same direction. And so what we end up with is that h dot h0 dot is just equal to r crossed with m v dot. So if we have the moment case, we have some moment and of course the moment has to come from a series of forces which are a distance away from the point we're considering, so we just put in bracket of forces. So essentially that's sum of the moments about a point which we'll call 0 for now. Well, it's equal to, if we've got forces acting on a body, there'll just be one distance r, okay? And then the sum of the forces acting on that body, m. Okay, so we have a situation like this. So we have that the moment is equal to the distance from the point that we're considering, and then the sum of the forces acting on the body. And we know from Newton's second law that we can rewrite that slightly, so this can be r crossed with mv dot, because F equals ma, isn't it? And a is equal to v dot, so the derivative of the velocity is the acceleration. So in fact, this rate of change of the angular momentum, the rate of change of the angular momentum h dot is actually equal to the sum of this moment m0 and we can also express this in a second way as well, as the moment of inertia multiplied by the angular acceleration, okay, where the angular acceleration is equal to the time derivative of the angular velocity, and in this case the angular velocity is equal to r crossed with v over r squared. And this moment of inertia of a rotating body is equal to m, the mass, times r squared. What I'm going to do is, I'm just going to, because I've used this r squared here is a generic term for radius of gyration, okay, so let's just put a little g here, because I don't want this to be mixed up with this r vector, okay, so this comes from the properties of the body. And also here where I've put this I, okay, I haven't put this as subscript 0, okay, because these things are relative to the point that we're taking in space. Okay, so when I drew the diagram, I drew like a little 0 as the point of where this is all happening about. So in general, we tend not to put that on. In a minute, you'll see that if it's about the center of the body, then we'll give it a different label. Okay, so this subscript is supposed to be telling you that it's relative to a point in space. Okay. So, in fact, that's the next thing to say. So if we have a rigid body, rotating about a center of mass, okay, which we'll call capital G, then the rate of change of angular momentum, hg dot, is equal to the sum of the moments around that point G, which is equal to the moment of inertia with respect to the rigid body, so Ig times the angular acceleration. So one more thing to say in general before we look at examples. If we have a rigid body, also for a rigid body, rotating about an arbitrary point P, then let's draw a diagram. Okay, so if we have some arbitrary point P, and that's going to the center of this rigid body, which is G. Okay, so the G is the center of mass. Okay, so there's some arbitrary body here, okay, which is rigid. And it's got a angular momentum vector in this direction. So this is hg dot, which is equal to the sum of mg, and it has some force vector which is m times ag. So this distance between P and G we're going to call rho G, that's a vector. Okay, so what we can say about this is we can now define a moment about the point P. Okay, so now the subscript is P as equal to the moments about G plus the distance from P to G times the sum of forces. So hopefully this is similar to the kind of mechanics you've seen before. If you've got moments acting on a structure, okay, and then you've got some force times a distance as well. Essentially what you're doing is you're adding the force times a distance, turning that into a moment, and then you're just adding that to the existing moments acting on the rigid body. Okay, so that's essentially what this is saying. Of course, we can write it in this slightly different way because we know the sum of mg is equal to this hg dot plus rho g times mag. For a planar system, which is what we're typically considering, we can simplify it again slightly. So we can simplify it to that the sum of the moments mp is equal to moment of inertia about g times angular acceleration plus rho g times m ag. And if we reduce this down to just scalars, so if on our diagram we draw the distance here, okay, so if we've got the forces acting through this line of here and we've got a distance d, then the simplest way to write this is that the sum of mp is equal to ig alpha. Sorry, these should not have, these aren't vectors now, plus the distance d times mass times ag. Let's say where d is the perpendicular distance between the point P and the line of the forces sum of F. So this is there's a lot here. Okay, so what I'm going to do is just try and do an example to show some of just to show how it works. Okay, and then there's also an example in the lecture notes as well. Okay, so let's try and do a relatively simple example to get us started. So let's just have a look at a 2D example. Okay, so we'll only ever be working with 2D examples, okay? We're using the same kind of format that we've developed of I, J, and K, okay? So let's do that now. So let's assume that we've got our I and J axes like this, okay? And then we've got a rotation around here, which gives us rotation around the K axis is coming out of the page, okay? So this is the rotation around this origin, which is we're assuming is sticking out of the page. Okay, so let's call this O here, this origin here. So that's O. Okay, we're going to have our mass M, okay, which is going to be here in this 2D plane. Okay, so the vector connecting up to it here is R, And of course we can decompose that into its x and y components, can't we? Okay, so we've got the x distance here and the y distance along here. And if we assume there's some velocity vector, again we can decompose that into its component parts, can't we? So we'll have a Vx in this direction and a Vy in that direction. So, and just to note that I and j are not rotating. Okay, so last time we did rotating stuff. In this case, they are not rotating. So, if we want to get the angular momentum, that's h0, okay, and that's equal to r crossed with mv. And we can, if we want to, we can take the scalar outside to make it simpler to just work out what's going on. So the scalar is the mass, so we can write it like that. It's the mass times the cross product of these two vectors r and v. Okay, so let's do the vectors so we know what's going on. So the vectors would be this. Okay, so x, y, and 0. Okay, so this is the components in the I, j, and k directions. Okay, so we've got a value in the x direction, we've got a value in the y direction, and we've got no value in the k direction because it's in the plane. So then v is equal to r dot, isn't it? Which is equal to dx by dt, dy by dt, and 0. And what we're going to do is, we've already labelled them in the diagram, we're going to call those components vx, vy, and 0. So then we can do the cross product. Okay, so we can do r cross with v. So we have our I, j, and k components at the top. So this is x, y, 0, vx, vy, and 0. And of course, this gives us x times vy minus vx times y in the k direction. Okay, so is that what we expect? Well, if you remember, the cross product of vectors gives you a vector out of the plane that the two vectors are in, so it's multiplied by the k vector, so this is basically in the k direction. If you want to view it as a rotation, you can view it as a rotation around the k-axis, okay? That's also a valid interpretation of, once you've got a numerical value, once you plug in some numbers, so typically in the questions you'll be answering, there'll be numbers to these quantities. Okay, you'll be able to plug the numbers in and you'll get some number times k. Okay, and that you can see that as a vector coming out of the plane. Okay, and because the mass is moving in the plane, essentially this vector is like a rotation around that k-axis, isn't it? Okay, so let's think about the rate of change of the angular momentum h naught dot. Okay, so when we did the derivative of this, we ended up with r dot crossed with mv plus r crossed with mv dot, and we said that this part was 0, didn't we? Because r dot is the same as v, and so we end up with something, a vector cross product with itself, which is 0. And so this is just m times r crossed with v dot. Okay, so it has the same kind of layout as this, except these bits of v dot, vx dot and vy dot, okay, in here. So we can see that r crossed with v dot would be equal to x vy dot minus vx dot times y, and again that's multiplied by the k direction. So this is a relatively simple example, just to give us a start of how you would actually calculate some of these quantities that we've talked about. In the lecture notes, there's a much more complicated example, isn't there? There's the car door example. Okay, so in this example what's happening is that there's a vehicle, okay, and the door of the vehicle is partly open, okay, and then you're asked to work out the rigid body dynamics of it, of what's happening to the car door based on some information that you're given, okay, and there's two methods shown of how to solve it in the notes. Okay, so what I want to do now is I want to give you a steer on this example, because quite often students look at it and they get scared that it looks really horrible, and it is pretty horrible, to be fair. Okay, so I want to give you some, rather than going through it necessarily right now, what I want to do is give you some background to it, and then you can look at it as part of your revision should you decide to, okay? So the first point to note, so points to note. So first thing to say is that this is a hard example. Okay? And what I mean by that is there won't be anything this hard in the exam. Okay? Okay, so if you look at this example and you're really worried by it and you think you don't understand it and it's too hard and what have you, take some deep breaths and stay calm, all right? Because it is a really hard example, and like I say, there won't be anything as hard as that in the exam. You might think the exam's hard, but I can tell you there won't be anything as hard as this in the exam, okay? That's a slight, your perceptions and mine are probably different, okay? So the best use of this example is if you're feeling like you really, getting to understand this, you've worked through the problem sheets, okay, and you think, I want to do a really tough example, I'm going to go through it and make sure that I understand it for my own benefit, then that's the best way to use it, okay? So what we'll say is use this example to stretch yourself, or stretch your knowledge, if appropriate, okay? So with that out of the way, there's some sort of technical stuff to just mention in this example. So I'll just write down a few technical points. So when you look at it, it may not be obvious, but there's no movement of the mass inside the rotating reference frame. So the V relative and A relative are 0. Okay, so that's it. So you remember last time we did that acceleration equation that looked pretty tough, didn't it? And it had all those different terms in it, the Coriolis and the centripetal and stuff. So you have to use that in this example. But there's some simplifying aspects, and this is one of them. So there is a choice about where to put the rotating axis. Okay, so when we did the rotating axis stuff, I tried to emphasize that when you're presented with a problem, quite often the axes aren't actually defined. Okay, and part of the skill of solving the problem is choosing where to put the axes. Okay, now in this car door problem, because it's quite a hard example, there's several choices which could work out. You know, it's difficult to tell in advance which is the right choice. Okay, so there are two choices. So they're the two different ways it's solved, with two different choices of axes. So the axes are either positioned at points 0 or G. Okay, now in the car door example, this means the car door is like this. Okay, so point 0 I think is there, and point G is here. So point G is the center of mass, like it was in the analysis we just went through. So in this case, the rigid body is the car door, right, which looks roughly rectangular. If we look down, this is looking down from above, right? So the car door can kind of move like this around its hinge. Okay, so I'm pretty sure, if I remember correctly, it's defined like this. So that 0 is the point of the hinge, okay, and G is the point of the center of mass of the door. Okay, and so there's some logic as to why you might choose the axes in those two different. You can see the logic of choosing it at the hinge, right? Okay, so because it's the rotating axes, then rotate with the door. But there's also another way of solving it with axes centered at G. Okay, and it goes through in detail in the PDF lecture slides to show you how that's solved. So depending on the choice, in one case, we end up with a distance rho, which is equal to r times the I vector, okay? And in the other, we have rho is equal to minus r times I. Okay, and that's the only reason for that change is because you've just moved where the axes are. Okay, so that's all it is. Okay, but often, this is a point that often causes a lot of confusion when people are trying to work out, going through the algebra of these examples and try and work out what's happening. So, final point we've made. I skipped past it. We just touched on it a little bit earlier, but there's this concept called radius of gyration. Okay, we haven't covered it in this course. I'm assuming that you can either you'll have done it in another course, or if you haven't done it in another course, it's a relatively simple thing. And I say Wikipedia has a very nice description of this as well. Okay, but what it is, it's like a property of the body. Okay, so it's related. So we can say if we've got a radius of gyration, which is normally written as r squared. Okay. It's a bit like variance is standard deviation squared or whatever. People say radius of gyration, but what they actually mean is the parameter r squared, and it's equal to the moment of inertia divided by the mass. Okay? Or, and I think we wrote this down earlier, the moment of inertia is equal to the mass times the radius of gyration. So you can think of this, if you have some rigid body, you can think of this as some distance coordinate. Okay, you've got a center of mass g. Okay, and if this thing starts to rotate, somehow this is some distance that's relating the distance out from the center, and showing how the it's characterizing what the rotation or the moment of inertia would be. So how much inertia does this thing get when it starts to rotate? It's encapsulated by that parameter there, and if you multiply that by the mass m, you get this thing called the moment of inertia. Okay? So, as I say, that example is in the notes. What I recommend is that you do the tutorial sheets 4 and 5 first. You'll find that tutorial sheet 5, which covers a lot of these type of problems as well, also gets really tough at the end. Okay, so if you get through 4, everyone should be able to do that. 5 gets tough. Once you start getting through 5, you could start looking at this example as well, because it's also quite tough. Okay, but by that point, hopefully, you'll have enough understanding of how to solve these types of problems, and it will make more sense. So, talking of tutorial sheets, I'll see you all at 4 o'clock on Friday to do more, yeah?